So we've got this cube that's expanding in volume. It may be air that's being pumped into a rubberized cube of some description, or it may be some kind of chemical reaction which is making it expand, or heat possibly, I don't know. So I've drawn a little picture of this cube and I've called the height of the cube h, for want of a better letter. Okay, the question tells us that the volume of the cube is increasing at the rate of 10 cubic centimeters per minute. So we can write down dV dt equals 10 straight away, a little simple differential equation. Now we're trying to find the rate at which the height is increasing. So that's dh dt. Now dh dt, using an adaptation of the chain rule, could be expressed as dh dv times dv dt. So this is what we're trying to find, dh dt. That's what we've got. So this is what we've got to find, dh dv. So we need a formula connecting h and v that we can differentiate. Well, if the height of the cube is h, then v is h cubed. Differentiating that gives dv dh is 3h squared. So dh dv is 1 over 3h squared. So we can then say that our dh dt is 1 over 3h squared times 10. But that isn't the value, that's just an expression for dh dt. We've got to find the rate at which the height is increasing when the volume is 300 cubic centimeters. So when v is 300, h is the cube root of 300. So we can pop that into there to find dh dt, and looks a bit messy, but the calculator can sort that out for us. So that gives us a relatively small increase in height of 0.07 centimeters every minute. So now we've got to find the rate at which a surface area is increasing when the volume is 500 cubic centimeters. So surface area. dA dt is the rate of increase of surface area, that's here, and we can express dA dt as dA dV times dV dt. Remember, we've already got dV dt, that's equal to 10. So how do we get dA dV then? We need an expression for A and V. So A is 6h squared here. So that's the surface area. We've got 6 faces, each one has got an area of h squared. So A is 6 times the cube root of v squared, because h is the cube root of v. So simplifying that, we get A equals 6v to the 2/3. Differentiating that gives us dA dV is 4v to the minus 1/3. So putting that into here now, to dA dV, we get an expression for dA dt, and then we need to put the value of v into this. Well, the volume is 500, so that gives us that many square centimeters per minute. That's the rate of increase of surface area. Now there is another way of doing this, slightly alternative. We can express dA dt as the product of 3 rates of change: dA dH, dH dV, and dV dt. So we have this expression here for A, 6h squared, so therefore dA dH is 12h. So we can put the 12h here. We've got dh dv from the first part of the question, 1 over 3h squared, and we've got dv dt here. So we can put all of those in to our modified expression for dA dt, and that gives us dA dt equals that. I'm not going to bother tidying that up too much. The h's cancel, but I then can put the value of h in. The value of h, when the volume is 500, the value of h will be the cube root of 500. So there's our, I did simplify it, 40 over h, and then we put the cube root of 500 into that. We get the same answer as before, thankfully. So two slightly different methods, both amounting to the same thing.